m by n matrix, a matrix with m rows and n columns, determines a linear map from Rn to Rm. Okay. Now, for instance, if I give you a matrix, if I give you a 2 by 3 matrix, so how about we use 2 by 3 matrix? If I give you a 2 by 3 matrix, the 2 by 3 matrix, I'm going to use A to denote the 2 by 3 matrix. If I use A to denote a given 2 by 3 matrix, I do not want to make the numbers too complicated. So now let's say 1, 1 to 1. So maybe 0, 1, 2. So simple enough. That's a 2 by 3 matrix. That's a matrix with two rows and 3 columns. Okay. Now I want you to recall, in general, a m by n matrix determines a linear map from Rn to Rm. In this particular case, a 2 by 3 matrix. Can I label that using 2 by 3 matrix? 2 by 3. A 2 by 3 matrix determines a linear map from R3 to R2. So don't be confused. You change the order. You kind of changing the order. Okay. A 2 by 3 matrix determines a linear map from R3 to R2. Okay. I will show you the linear map. The notation I used last time was T sub A, right? T sub A is a linear map from R3 to R2. 2 by 3 matrix determines a linear map from R3 to R2. Okay. And the rule is given as follows. Every vector in R3, we call that domain, we call that codomain, right? Every vector in the domain has 3 components. Every vector in R3 has 3 components, right? So the rule is given as follows. Every vector in R3 is with 3 components. So now let's say x, y, z. Actually, you could also use ABC, whatever thing representing any vector in R3 in the domain. Okay. Every vector in R3 is mapped to, we use a notation like that to denote it's mapped to, okay, or goes to. You can just think goes to. Every vector in R3 goes to the vector. In terms of the matrix A, goes to the vector computed using A times x, y, z. I'm talking about that for the right hand side. The right hand side, you compute the matrix A times x, y, z. You are hoping to get a vector in R2, right? So because R2 is the codomain, R2 is the codomain containing all the outputs. Okay. You are looking for a vector with 2 components. So by that we mean you multiply the 2 matrices. A is the matrix. So now let's say the first row 1, 1 to 1, the second row 0, 1, 2, right? So that's the given matrix A. And then you multiply that on the right by x, y, z. If you do everything right, you are going to have a vector in R2. You are going to have a vector in the codomain, so with 2 components. Okay. I'm running out of space, so can I just write the answer outside the circle? That's quite paper. Okay. Again, the answer has 2 components. The first component is computed using the first row of the matrix A times the column consisting of x, y, and z. So by that we mean the first component here is x and then plus 2y, right? And then plus 1z. Okay. And then you use the second row to multiply the column consisting x, y, and z. I think you have y plus 2z, right? You have y plus 2z. I do know all of you guys have no problem to multiply 2 matrices. Okay. I believe you can follow me. Again, the point is every matrix, a 2 by 3 matrix, so in general a m by n matrix, determines a linear map from Rn to Rm. Okay. A 2 by 3 matrix determines a linear map from R3 to R2. And of course, for the answer, you have to write out the answer. Okay, so the answer, by that we mean this line is the definition of the linear map. Okay, the next line will give the rule. Okay, the rule is given, so something like every vector in R3, every vector with 3 components is mapped to you. We just computed that, right? The first component is x plus 2y, and then plus z, and then the second component is y plus 2z. That's the main thing we did the last time. Okay. Also, I mentioned how to interpret that. It's useful later. It's useful very shortly. So probably in next class. Okay. I want you to see the output, that way, in terms of the component. In terms of the components, I mean. Okay. Each vector with 3 components is mapped to the output. In the output is the first component of the input, and then plus twice the second component, and then plus the third component. I want you to see that way. Okay. And likewise, the second component is in here is the second component in the input, and then plus 2 times the third component in the input. So that's how you get the second component of the output. Okay. And then we keep on going. The main thing today, I'm going to show you actually every linear map is associated with a matrix. It's kind of the other way around. For the thing we did the last time, I gave you a matrix. I'm looking for the linear map. Okay. For the thing we are doing today, I give you the linear map. I'm looking for the matrix, the other way around. After that, then you are going to see all the matrices and all the linear maps are one-to-one correspondence. So by that we mean each matrix determines a linear map. The other way is also true. Okay, each linear map is determining a matrix. That's why we can use matrices to study the linear maps. But before we do that, now let's take a look at a conclusion on the next slide. Now look at this. Okay. The statement is kind of weird. But I will show you the meaning. Okay. The meaning is that as long as you know, okay, you look at T. Now suppose we are looking for a linear map T. It's from Rn to Rm. So what are these? You look at the screen. So what are these? On the left hand side, you have all the standard basis vectors. So do you know what I mean? Actually, for instance, in R3, the standard basis vectors are I and k. I believe you can recall that. Okay. In this particular case, these are the vectors, standard basis vectors in Rn. N can be anything. Okay. N can be 4, N can be 5, N can be anything. Okay. You look at these. These are the outputs of the standard basis vectors. Okay, now the idea. Now you listen to me carefully. The idea is that as long as you know the outputs of all standard basis vectors, and then you know the linear map, there's a linear map determined by the outputs of standard basis vectors. Okay. I want to repeat, as the meaning of the statement is that as long as you know the outputs of standard basis vectors, then you can determine the linear map. We're going to see how, and then we go back to the general conclusion. Okay. So how about we work on question 1? Okay. In question 1, you do not know the linear map. We are looking for the linear map. Okay. You do not know the linear map. So can I use the notation T sub A? T sub A. So how about I just use T? Okay, I will just use T for this question. You do not know T. You do not know T. Okay, so, but you know the output under T for the standard spaces vectors. In R2 you have 1 0 0 1. So these two guys are standard basis vectors, right? You do not know T, but you know the outputs of 1 0 and 0 1. Okay. Using the conclusion, we are going to see we can get the linear map. So, but before that, we get the matrix first. Okay. Now, let's go back to the conclusion to see how to form the matrix. Okay. The matrix is formed by putting all the outputs, I mean the components of all the outputs, in columns. That's how you get the matrix. I want to repeat. To form the matrix, we form a matrix first, and then the linear map is determined by the matrix. So we'll see that very shortly. But now let's concentrate on how to form the matrix. Forming the matrix by putting the components of all the outputs of standard spaces vectors in columns. That's how you get the matrix. I will show the meaning. Okay. Now the solution. We form a matrix by putting the components of the outputs in columns. I mean the outputs of the standard spaces vectors. So A is formed by the output of 1 0, so which is 1 0, right? I mean you look at the mouse cursor, that's the output of 1 0. In this column you have the output of 1 0. Okay. The second column is the output of 0 1 of J actually. Okay. So the second column you use -1 0. That's how to form the matrix A. Okay. Actually, we are done the first part of the question. We found the matrix associated with the linear map. Okay. In the second part, we also found the map. Okay. Now let's recall every matrix determines a linear map associated with the matrix. In particular, A is a 2 by 2 matrix, so A determines the linear map. Okay. Now T is the linear map associated with A. Now let's recall how we did that. Okay. So T is the linear map associated with A is from R2 to R2. Okay. You can see it either way. A 2 by 2 matrix determines a linear map from R2 to R2. So this time I hope it's not too confusing. Okay. And the given map we are looking for is actually the linear map associated with A. So we just compute that. Okay. And the rule is given as follows: every vector with two components in R2 is mapped to, in general, is mapped to A times xy, right? That's the definition we just reviewed. That's the definition of the rule. In the next line, we actually gave the rule. We gave the rule, I said. Okay. The rule is calculated by xy goes to A times xy. So in this particular case, we got A. That's why we want to. That's why we found A. Eventually, we want the linear map, right? On scratch paper, A times xy, we compute that. A times xy is computed using 1 -1 0 0. I think I got it right. Then times xy, right? You treat the two things as two matrices, right? The first one is a 2 by 2 matrix. The factor on the right is a 2 by 1 matrix. You treat xy in column as a 2 by 1 matrix, and then you multiply the two matrices. We have seen this many times already. Okay, the first row, I believe the first row is x minus y, right? The second row is 0. Did I got everything right? That's not something in my mind. So, but that's how it works. So we'll see it very shortly. Probably it is the thing. Okay. Again, the first row is when we say vectors, we say the first component. The first component is x minus y. Okay, and then the second component is 0. Give me one little moment. So anybody see anything wrong? Yeah, probably. Yeah. So that's the question. That's the question. Okay. Okay. So we're done the question. I'm not going to talk about the geometric meanings using that. Actually, that was my intention, but this one is not too convincing. I'm going to use some other questions to talk about the geometric meaning. Okay. We're kind of done the question, but yeah, in order to convince you, I'm going to add one more step. Okay. So how about I just tell you justify the answer. Okay. If I include justify the answer. Justify the answer. By that we mean I do want you to verify the linear map T we found indeed I mean the output of 1 0 under T is indeed 1 0, and then the output of 0 1 under T is indeed negative 1 0. Okay. Now let's justify that. Okay. So maybe to justify we compute the output for the input of 1 0, the standard spaces vector. Okay. So by that we mean so this time I'm going to use another notation I told you last time. This notation is for the notation of the output for the input of 1 0. So we compute that first. Okay. Again, I want you to recall the meaning of the output. Okay. So you look at the mouse cursor. This notation, it means the output for the input of 1 0 under T, the output for the input of the vector in R2 under T. Okay. So this time you write equal sign, and then the output, you look at the rule in here. It's computed using that. You look at the mouse cursor. The output is computed using that formula. Can I say formula? Using that formula. Okay. The first component is computed using the first component in the input minus the second component in the input. I believe you can see. So basically, x value is 1, y value is 0. You use that formula. Okay. 1 minus 0, I believe you have 1, right? And then the second component is always 0. And then you have to verify that too. Okay, for T. By that we mean you have to show me 0 1 goes to negative 1 0 using a new notation. The output for the input of 0 1, the output for the input of 0 1 using the formula. So we just got in here. It's computed using x minus y. X minus y is the first component minus the second component. So you have negative 1, right? And then the second component is 0. Okay. Again, I was trying to talk about the geometric meaning of this of this linear map, but it's not too convincing. I probably can go back to that. Okay. So any questions? To do the question, form a matrix first, okay, and then you get the linear map associated with the matrix, as we did the last time, and then you have the linear map. Okay. To justify, you just verify 1 0, so goes to 1 0, and 0 1, so goes to negative 1 0, as intended in the question. Okay, if you don't have any questions, we'll move on to question 2. Question 2 has no geometric meaning. Yeah, probably it has, but it's very hard to describe. We just do the question. Okay. Question 2, you can treat question 2 as with the intention that showing you how to use the conclusion. In question 2, we are looking for a linear map from R3 to R. I have a typo in here. From R3 to R2. We are looking for a linear map from R3 to R2. This time I'm going to change the notation to T as well, for a reason I can probably tell you later. So we are looking for a linear map T. The linear map is denoted by T. It's from R3 to R2. Okay. I told you before, the key thing is, as long as you know the outputs of the standard spaces vectors, and then you can determine the linear map. In this particular case, we have 3 standard spaces vectors in R3, right? So that's 1 0 0. Using the notation we used before, that's I, that's J, that's K. Okay. If we are given the outputs of I, J, and K, and then we can determine the linear map. So that's the whole idea. Now the solution. In any case, form a matrix first. The matrix is formed using the outputs of I, J, and K in this particular case. So maybe let A be the outputs of standard spaces vectors. The output of 1 0 0 is 1 2. You put 1 2 in first column. And then the output of 0 1 0 is 3 4. You put 3 4 in the second column. And likewise, the third column is 5 6. Right? Get the matrix first. And then in the question, the second part, we are looking for the linear map. So we are looking for T. To get T, you tell me 3 things. You tell me the domain, right? You tell me the codomain. You tell me the rule. Okay. The domain is the set consisting of all possible inputs. The codomain is the set containing all outputs. And the rule will tell you each vector in the input goes to what? Okay. In output. Again, so this time T is the linear map associated with the matrix A. We used to use T sub A, but in here we just use T. Okay, so T is from. You look at T. Okay, in here in the question we are looking for a linear map from R3 to R2. Now A is a 2 by 3 matrix. A 2 by 3 matrix determines a linear map from R3 to R2. Right? I said that many times. Okay, so T determines a linear map from R3 to R2, right? Now the rule, the machine. I think I used the term machine last time. Okay, a machine can process inputs and producing outputs. Okay. If I give you the input, so now let's say X, Y, Z. Again, the notation is not unique. You could use A, B, C, but in most cases we use X, Y, Z to represent an arbitrary vector in that R3. Okay. The output is computed using the formula we mentioned. So in the conclusion, I will show you the conclusion again. Okay. Actually, I believe you can remember. It's computed. The output is computed using. The output is computed by multiplying the given matrix A. So the matrix A we found, and then times x, y, z. You treat that as the product of two matrices. Okay. That's the definition. So, but to give the answer, you have to compute A times x, y, z. This one. So can we do that mentally? So this time you have the matrix A, and then you use A to multiply x, y, z with x, y, z on the right. Okay. Can anybody tell me the answer? Can anybody tell me the answer to the first component? I'm looking for the first component on the right hand side, please. Yeah, x plus 3y and then plus 5z. Yeah, that's it. This time you look at here. Okay, A is, we found A in here. You use the first row of A, 1, 3, 5 to multiply that column, the column consisting of x, y, and z. Okay, you have 1 times x, 3 times y, 5 times z. Yeah, that's how we get the first component. Okay. And then the second component, I believe you got it. Okay, 2x plus 4y and then plus 6z. So thank you. Okay, so that's the linear map we found. Okay. Again, using the given condition, we got a linear map T, and then we have to justify. So can I include one more step? I want you to justify. Okay. We want to show, to justify, by that we mean we want to show T indeed maps 1, 0, 0 to 1, 2, 0, 1, 0 to 3, 4, and so on. Okay. So maybe to justify, under the given, so linear map T, under T. Okay, under T we do have, so this time you do not look at the top, you look at the row only. Okay, you look at the row only. We want to verify it's indeed true that 1, 0, 0 goes to 1, 2. You look at here. Okay, 1, 0, 0, it means x value is 1, y value is, I mean x value is 1, y value is 0, z value is 0. Okay, and then you get the output. So did I mess anything up? You get the output. Okay, so basically 1, 0, 0, so it goes to 1, 2. Do we have 1, 2? I think we do have 1, 2. Okay, and 0, 1, 0, 0, 1, 0. The second vector, actually that's j, right? J goes to 3, 4. I was confused for a little moment, but now I think I got it. 0, 0, 1 goes to 5, 6. Now now I hope so you're convinced. Okay, this linear map found that way indeed is the required one. Okay, we want a linear map T satisfying the conditions, right? Now we found a T satisfying the conditions. Now we're done. Okay. So that's question 2. Okay, it's kind of boring at this time, but cheer up. I will show you some interesting ones. If you like math, the following could cheer you up. This time we include some geometric meaning. Okay. So this time we are looking for a linear map that rotates every vector in R2 clockwise. Clockwise. You know the clockwise, right? You look at the mouse cursor. Clockwise, I believe it's that way. Clock, so it goes that way, right? Clockwise by 90 degrees. Later on, I'm going to make some comments, but now we are going to get the linear map first. Now the solution. So anybody can guess what we do? How can we start it? How can we get started with the question? To determine a linear map, we need a matrix. To determine the matrix, we need the outputs of standard spaces vectors. We start from that. So the first thing we do is to get the outputs of I and j. Okay. So this time I'm going to use some notations. Okay. So maybe I'm going to use I to denote 1, 0. Right. Standard basis vector, one of the two. Okay. And then I'm going to use j to denote 0, 1. Right. We have seen the notation many times. So basically, again, I and j are standard basis vectors in R2, right? So maybe I'm going to use a notation to denote the map, the linear map I'm looking for. Okay. So maybe let t. Of course, t is from R2 to R2. Be the required. So I can say required linear map. By that I mean t rotates every vector in R2 clockwise by 90 degrees. Okay. This time we are going to draw something in R2. Okay, on Cartesian on rectangular coordinate plane. So do you remember I is here? I mean for the position vectors, the vector I is here. The vector I has two components, 1, 0, right? And likewise, the vector j is here. The vector j as a position vector has two components, 0, 1. Right. Alright. Yeah, probably I do not have to. It's kind of messy now. I'm going to remove the components. Anyway, that's I. Okay, I'm going to draw j in here. Now you look at t. T is a linear map that rotates every vector clockwise by 90 degrees. So by that we mean, so can anybody tell me the output of I? The output of I. The output of I is the output of every 0, 1 is right. 0, -1, 0, -1. Okay. I will tell you why. Okay. The output of I is found by rotating the given I clockwise by 90 degrees. Okay. Now you look at the screen. That's the vector I. If you rotate I clockwise by 90 degrees, you have a vector in here. This is the output for the input of I. So that's Ti, right? That's Ti. So what's Ti? If you are looking for the two components of Ti, Ti has two components. The first component is x coordinate of that point, which is 0. Y coordinate of the point is 1, right? I mean the terminal point. So Ti has two components. So now let's say 0, -1. 0, -1. I will see if you got it or not. So maybe some other guy, so not current. Some other guy. So tell me the output for the input of J. For the same reason, you rotate J clockwise by 90 degrees. I'm looking for the output for the input of J. Okay, it's J is 0, 1. J is 0, 1. So try again. J has the components of 0, 1. If you rotate J clockwise, if you rotate J clockwise by 90 degrees, so what's the output of, 1, 0 is right. 1, 0 is right. Okay, I will tell you the interesting part. Very shortly, I will convince you, okay? But now I want to tell you the conclusion. If T, a linear map, rotates I and J clockwise by 90 degrees, later on you're going to see T will rotate all vectors clockwise by 90 degrees. So basically, by the linearity, the property of T on I and J will determine the property of T on any vector. So you're going to see it very shortly. Okay, so we found the outputs for the input of I and J. Now using the notations we have just seen, it means the vector I 1 0 goes to 0 negative 1. I'm trying to connect what we have found, what we observed, to the notation in the conclusion. So by that we mean 1 0 goes to 0 negative 1, okay, and then 0 0 1 goes to 0 1 goes to 1 0. Okay. For the notations, these two things are equivalent. You look at the mouse cursor, okay. This line is equivalent to that line. This the top line, the first line is kind of the function notation, okay. The second line is kind of the new notation we introduced last time. Okay. In any case, we are looking for a linear map. Okay, a linear map. Now we can form a matrix now, right? Now let A be the matrix given by the outputs of the standard basis vectors. But I mean, A is formed using the output of the first column has 0 0 negative 1, right? 0 negative 1, so we have seen that many times. The second column has 1 0, right? We set A to be that. After getting the matrix, a matrix can determine a linear map. Okay. And then I will try to write everything on this slide. A will determine a linear map. So can I use T to denote the linear map? Then T is A is a 2 by 2 matrix. So T is a matrix. T is a linear map from R2 to R2. A 2 by 2 matrix determines a linear map from R2 to R2. Okay. So this time I'm going to write the rule so directly. Okay. I still want to write it in 2 lines. So the rule is each vector xy is mapped to the vector I'm trying to save space. I think it doesn't matter. Okay, each vector in the domain xy is mapped to a vector in the codomain. It's given by A times xy, right? By that we mean each vector. So now let's say xy goes to the vector. Now let's compute the right hand side. Okay. The right hand side, if you multiply A and xy, you are going to get the first can you double check it for me? I think the first component is y, is that right? And the second component is negative x. I think I got it right. Okay, I'm going to repeat my point. Okay, as if a linear map. Now let me try again. If a linear map rotates every, I mean, now let me try again. I think I messed something up. If a linear map rotates I and j clockwise by 90 degrees, then t will rotate all the vectors clockwise by 90 degrees. So how about we just check that? Okay. So we're kind of done the question, but I'm going to show you my point. I will show you my point. Okay. Now let's verify this t is indeed as required. Under t, that's not part of the solution, but we're going to get some outputs for some particular inputs. Okay. So can I just say under the linear map t? Now let's try to get the output of 1, 1 in two ways. So maybe the first way is to use the definition here. I mean, using the rule in t. X value is 1, y value is 1. I believe the output is y value 191, right? So the output is 191. So can I use v to denote the vector 1, 1? I think the vector 1, 1 is here. That's the vector v. V has the two components 1, 1. Okay. And then, so where's 191? I believe 191 is here. That's the output of v. That's the output of v under t. So do you see the output tv? I mean t in brackets v, of course. I mean the output of v. I'm trying to say under t rotates v clockwise by 90 degrees. That's what I'm trying to say. So do you see that's 90 degrees? You look at the mouse cursor. T rotates v clockwise by 90 degrees. Okay. I think it's true for the particular vector 1, 1. That's what I'm saying. Okay. I want to convince you. So how about we use another vector as the input? So now let's say whatever vector you want to choose. So how about we use so 91, 2. According to the calculation, 91, 2 should go to y value, and x value is 91, y value is 2. Okay. I think it will go to 1. Sorry. I think it goes to 2. 2, 1. 2, 1. Is that right? Sorry. So you're smarter than me, of course. I'm really slow at numbers. I think I could tell you why. I'm really slow at numbers. Since the graduate school, I have been doing proofs all the time. I rarely use numbers. Actually, so of course I have been using numbers so since teaching, but still I'm not good at numbers. Okay, now I want you to see one other vector. Okay, if the input is -1, 2, now you look at here, if the input is -1, 2, I think the vector with the first component of 91, the second component of 2 is kind of here, right? You look at the output. The output is has the first component of 2, the second component of 1. Did I mess anything up? The first component of 2 and the second component of 1. If I'm going to use w to denote the vector 91, 2, that's the output for the input of w. So you see it's also true t rotates that vector w clockwise by 90 degrees as well, right? Okay. Interesting now? I believe now you can be convinced t will rotate every vector with two components components x, y clockwise by 90 degrees. Any questions about that? I spent a pretty long time on that. It's because I think it's kind of interesting. Okay, now let's work on a very similar question. Okay, very similar question. So later on, you're going to see linear transformations. I said linear transformations. You're going to see the definition soon. A linear transformation from R2 to R2. A linear transformation on R2 is actually a linear map from R2 to R2. By that we mean if the domain and the codomain are the same, then we say it's a linear transformation. Okay. So because I said the term, I will tell you the meaning. Actually, in question 4, we're going to see another linear transformation, right? It's from R2 to R2. This time, there's a geometric meaning too. Okay. I'm trying to say, in many cases, linear transformations, they can be a rotation. So we have seen a rotation, right? Can also be a reflection. But transformation in general is not a linear transformation. I don't know, you know what I'm talking about or not, but in geometry 3 transformations you can do. One is I was trying to say the last one is a translation. Okay, in geometry the 3 operations on a plane figure you can do. One thing is a rotation, right? The other thing is a reflection. The third thing is a translation. Okay. So now let's say you have a triangle, something like that. If you do a rotation, I believe you know the meaning of the rotation. So can I use that point? Use A to label that point. So that point is B. So that point is C. If you do a rotation, you have something like this. So now let's say A goes to here, B goes to here, C goes to here. That's kind of a rotation. Illustration only. Okay. A reflection. And so now let's say if you have a triangle in here. So now let's say that way. If I want you to reflect above the horizontal axis, so what do you have? The reflection is something like this, something like that, right? Reflection. And the translation is something like the following. If I give you a triangle something like this, A, B, C, a translation, it means you move the triangle to in some direction. I said, okay, in some direction by some distance, you have a translation. I was trying to say in general a rotation and reflection. In general, the map is linear, but the translation is not. You do not have to fully understand what I just said. Okay, you just need to be able to do questions. Sorry, I'm a bad teacher. I need to teach you why and how. But anyway, we're going to get this. Now the solution. So this time I'm going to let T be the required linear map. Can I use the term linear transformation? Again, when the domain is the same as the codomain, we call it a transformation, a linear transformation. Okay. Do I have to introduce I and J? Actually, I and J are standard notations. I really do not have to introduce those. Okay. And then, in order to get the matrix, we need the output for the input of I. and we need the output for the input of j. So we have to compute this. Okay. We look at the meaning of t on scratch paper. We figure out the meaning of t. Actually, on rectangular coordinate plane, you have a line. Line is y is equal to x. You know the line, right? For the people in calculus, you really should know the line. For the people who are not in calculus, I want you to recall that equation. The graph of that equation is a straight line. It's a straight line. The straight line is kind of that. I think you can recall that. So this time we're going to reflect every vector above that line. Okay. So anybody want to tell me I is here, right? So that's I. I has the two components 1, 0. So anybody want to tell me the output for the input of I? I was trying to write the output for the input of I. So that's my I. Sorry. Anybody want to tell me the output for the input of I in terms of components? The 0, -1, right? The line of rotation is here. You just imagine that's a mirror, and then where's the image in the mirror? I is here. You reflect I above the line. So try again. So 0, 1 is right. 0, 1. Yeah, that's probably what you meant. Okay, I want to repeat. You rotate, not rotate. You reflect I above that line. So this line has the equation y equals x, right? You reflect I above that line. That's the output for the input of I. So this one is the output for the input of I. So this one has two components. You just told me. Gardeep just told me 0, 1. I think 0, 1 is right. And likewise tj. I mean the output for the input of j under t. So that's the full name. I'm looking for the output for the input of j under t. This time I think you have 1, 0. Right. I mean this vector is the output for the input. Yeah, I think I got it. This vector is for this I is also the same thing as the output for the input of j. That's what I'm looking for. Okay, so by that we mean by that we mean under the linear map T 1, 0. So that's I, right? 1, 0 goes to 0, 1. 0, 1 is the output for the input of 1, 0. And also 0, 1 is j. 0, 1 j goes to 1, 0. You just do a reflection above the line. I believe you can see what's going on. Now the rest should be simple. We form a matrix. We have seen that many times. I'm going to do that a little quicker now. We form a matrix. The matrix has two components. The first component, I hope I'm not lost. The first component, the first column. The matrix has two columns. The first column has the components 1, 0, so which is the components of the output of 1, 0. I said 1, 0. It's 0, 1. And the second column has 1, 0. I think you'll see what's going on. So correct me if you see anything wrong. We form a matrix A like that, and then A determines a linear map. according to the conclusion we have seen, the linear map T we are looking for is the linear map determined by the matrix A. It's from R2 to R2, of course, right? And I will write them in rows. Every vector x, y, z, x, y. You have to take a vector from the input. Every vector in the domain has two components. X, y goes to, this one should be simple. Yx, right? Yx, you switch the two components, right? I'm not going to run too fast. It's because for the quiz or the assignments, I'm looking for that line. Okay, each vector x y according to the definition goes to A times x y. Okay, this means each vector x y goes to yx. By that we mean you multiply A and xy, you have yx. I believe. Okay. So does that make sense? If you switch the components and then it's a reflection? I'm trying to say it's true in general. Okay, it's true in general. So now let's say if you have a vector, I will give you a more convincing one. If you have a vector, so now let's say 1, 2, okay, call that vector u. U has two components of 1, 2. Okay, U has two components of 1, 2. And then if you switch the two components, if you switch the two components, you are going to have 2, 1. I believe 2, 1 is here. Can I say Tu is the output for the input of U under T? So do you see it's a reflection about the line y equals x? Again, question 4 is designed to show you in many cases a reflection about some line passing through the origin is linear, a linear map. Okay. So that's question 4. I think we are running pretty slow today. It's because I made many comments. Very interesting things. Okay, now let's work on question 5. Okay. For question 5, I'm going to make my point. Okay. I told you earlier, the main thing we are doing is the other way around. Okay. Last time I told you each matrix determines a linear map. So this time I'm going to tell you each linear map is determined by a matrix. So can I say that way? We can associate each linear map with a matrix. And then after that, so you are going to see there's a 1-to-1 correspondence between linear maps and the matrices. So that's why we can use matrices to study linear maps. Okay. But before that, I'm going to we're doing question first. Now the solution. Now let's work on question T. Now let's work on T first. In T, on this line, I guess you know what I mean. Okay. For T is linear. It's from R2 to R2. Each vector xy in R2 is mapped to that. And using the definition of T, now we are going to get a matrix. So that's a question. Okay. You look at the question again. We're looking to get the matrix associated or determined by T. So in this particular case. Okay. Now the solution. So maybe we'll do one question at a time. Now let's concentrate on t first. Okay. So maybe for the first one, so I'm going to copy t. So maybe for t, from R2 to R2, the domain is R2. The codomain is also R2. Okay. So this time the rule is given as follows: every vector with two components, every vector in R2 is mapped to the vector with two components, 2x and negative y. Okay. For this one, we are going to get a matrix. How can we get the matrix? Anybody want to tell me briefly how can we get the matrix? You think what we need to get the matrix? We need the outputs for I and j, right? So we'll do that first. Okay. For t, we have, in any case, we want to get the output for the I and j first. Okay. I is the vector with two components, 1, 0, okay, standard basis vectors, and the j is the vector with two components, 0, 1. I did nothing but listing the two vectors. I mean the two standard basis vectors. Okay. And then, so tell me, under t, 1, 0 goes to what? I'm looking for the output for the input of I, using the definition piece, using definition of t. In this case, x value is 1, y value is 0. Yeah, that's 2, 0, 2, 0, 2, 0. You look at the mouse cursor. You look at that line. Okay. For 1, 0, for I, x value is 1, y value is 0. Okay. 1, 0 goes to 2x negative y. 2x is 2 times 1. Negative y is negative 0. Of course, it's 2, 0. Okay. And likewise, 0, 1 goes to 0, negative 1. Is that right? 0, negative 1. Sure. Thank you. Cool. Again, originally in the question we are looking for a matrix. The idea, okay. So by that we mean to determine a matrix, we need the outputs for the inputs of I and j. So that's what we are doing now. Okay. Okay. So what? So the matrix associated with t associated with t. Associated with t, with the, I did it right. Okay. The given map. So linear map. The given map. Okay. Is, can I use A to denote that? Is the matrix A. The matrix A formed by the outputs of and j. Okay. The components of the outputs of and j. So the first column has 2, 0, and then the second column has 0. So 0, negative 1, right? So that's the matrix. If I include one other question, so maybe if I want to justify, okay, to justify, you want to show the given t is indeed the linear map associated with A. Okay, to justify. We get the linear map associated with A. Okay, so we compute T sub A using the notation I used last time. Okay, A is a 2 by 2 matrix. A 2 by 2 matrix determines a linear map from R2 to R2, right? From R2 to R2, and the rule is given as follows. Okay, the rule is given by xy goes to A times xy. Okay, A times xy. So this time I actually want you to compute A times xy as the product of two matrices. Okay, it means xy. Right, that is i.e. it means xy goes to. Do not look at t. Okay, do not do not look at T. Now I want you to use the matrix to get T sub A, the linear map, so determined by A. And you compute A times xy. I believe you have 2x minus y. Is that right? This means the linear map determined by the matrix A is indeed the given T. So T sub A, the linear map associated with A is indeed the given linear map T. Okay. We'll do this question only once. I just to convince you. Okay. I just to convince you the linear map found that way. I mean the matrix found that way indeed determines the given linear map. Okay, so we're done. We're done the question for T. Any questions? If you don't, we'll move on to work on T1 and get all others. Okay, so maybe for T1, you just repeat the same thing. Okay, maybe for T1. T1 is actually from R3 to R3 this time. I will copy T1. Okay, the rule is given by each vector in R3 x, y, z goes to x plus y, y plus z, and z plus x, the last component. Okay. The idea is to do what? To get the matrix associated with T. In order to do that, we get the outputs. I was trying to say under T1. Under T1, in order to get the matrix, we need outputs for I, j, and k, right? I mean, I is the vector with 3 components, 1, 0, 0, right? 1, 0, 0 goes to, you treat x value to be 1, y value to be 0, z value to be 0. I believe the output, so anybody, so double check for me. I believe the output is 1, 0, 1, is that right? 1, 0, 1. Sorry, 1, 0, 1. So this time you look at T1. Okay. The output for the input of 1, 0, 0 is 1, 0, 1. For the people who might be confused, I will show you. You look at the mouse cursor, okay? The mouse cursor, x value is 1. We're trying to get the output for the input of 1, 0, 0. So you treat x value to be 1, y value to be 0, z value to be 0, okay? So 1, 0, 0 goes to x value is 1. The first component is 1 plus 0 is 1. The second component 0 plus 0, 0. The third component 0 plus 1, which is 1, right? Simple. Okay. And then we also need to get the outputs for j and k. J has 3 components, 0, 1, 0, right? And k has 3 components, 0, 0, 1. To get the outputs for j, you treat x value to be 0, y value to be 1, z value to be 0. Okay, I think you have 1, 1, 1, 1, 0. Is that right? And the 0, 0, 1 goes to 0, 0, 1 goes to x value 0. 0, 0, 0, 0, 1 goes to 0, 0, 1. Sorry, it's 0. I think I did something wrong. 0, 0, 1 goes to 0, 1, 1. Again, x value is 0, y value is 1, z value is... I said something wrong. Now let me try again. Again, you look at the mouse cursor. X value is 0, y value is 0, z value is 1. So the second and the third components in the output are 1, 1. I mean the matrix. Now we can get the matrix associated with T1. So the matrix associated with T1 associated with T1 is the matrix 1 0 0 1 0 1, the first column, the second column 1 1 0, the third column 0 1 1. Okay, simple. I'm not sure if you want me to go over all these questions or not. So, but why not? Now let's go over all these questions. Each question is trying to make a point. Okay, now let's work on T2. Okay, so this time we work on T2, the circled one. Okay, so maybe for T2, I'm going to write a little less. Okay, for T2, we are trying to get a linear map from R3 to R2. So this time, R3 is the domain. So to form the matrix, you need the outputs for the inputs of ij and k. You have 3 standard basis vectors, right? Yeah, 3. So you need to get the output for the input of 1 0 0, 0 1 0, and 0 0 1. We'll get them one by one. Okay. The outputs are in R2. I mean, for each vector in R, for each vector with 3 components, the output is a vector with 2 components. Okay, 1 0 0. You treat x as 1. You treat y as 0. You treat z as 0. I believe the output for the input of 1 0 0 under T2 has the first component of 1. Is that right? The second component of 0. So correct me if you see anything wrong. Okay. 0 1 0. 0 1 0 goes to x value is 1, y value is 0, z value is, y value is 1. I think it goes to negative 1. 1, is that right? And 0 0 1 goes to x value is 0, y value is 0, z value is 1, 0, 0 negative 1. Anybody see anything wrong? Okay, now the matrix associated with T2. Now we are ready to get that. So the matrix, so can I just write the matrix we are looking for is the matrix associated with T2. Okay, is 1 0, the first column. The output of I 1 0 0 goes to the first column. The second column negative 1 1. The third column 0 negative 1. That is the matrix, right? Okay, now T3. Now we work on T3. For T3, we are looking for T3 is from R2 to R3. The domain is R2. The codomain is R3. So by that we mean the inputs have 2 components. The output has 3 components. I hope it's not too weird. Okay. In order to get T3, we need the outputs for the inputs of I and j in R2. Okay. Standard basis vectors. X value is 1, y value is 0. So in the output, the output for the input of 1 0, the first component is 1, the second component is 0. I believe it's 1 1 1 1 2. If you replace x with 1 and y with 0. I think you have 1, 1, 2. Okay. And likewise, the second component is I mean the output for the input of 0, 1. The output for the input of 0, 1, x value is 0, y value is 1. Okay. I think you have negative 1, 1, 3. Is that right? So correct me if you see anything wrong. Okay. So the matrix we are looking for. The matrix is the matrix associated with T3. The matrix has 2 columns. One column is 1, 1, 2. The components of the outputs of 1, 0. I mean the components of the output of 1, 0. Okay. The second column has components. The second column are negative 1, 1, 3. So that's the matrix. Okay. Now for the notation. Okay. So because there's a 1-to-1 correspondence between matrices and so linear maps. In the future, so now let's say if I give you, I will make the comments on a new slide. In the future, it makes sense if I give you a matrix A. So now let's say 1, 2, 3, 4, a 2x2 matrix, 1, 2, 3, 4. So because there's a 1-to-1 correspondence between matrices and so linear maps, in the future I just use A. I'm not going to use T sub A or T. I just use A to denote the linear map from R2 to R2. I'm trying to say I'm going to use one notation for 2 things. One notation for 2 things. One thing is a 2x2 matrix in this particular case. So the other thing is the map, so determined by A. It's not confusing. There will be no confusion. I'm trying to say if you write A in that form, you know A is a map, right? It has domain and codomain. If you write A as in that form as an array of numbers, then you know A, it means a matrix. Again, in the future, I'm going to use A for 2 things: a matrix, a linear map, right? So those are my comments. Okay. I made some comments on notations. I'm trying to say in the future, we'll use A to denote both matrix and the linear map associated with the matrix.